atmospheric rivers?
Yes. Yep.
And when he came here, he was already very interested in forecasting avalanches. He came here to work on a wildlife project, and he ended up figuring out a way to put wildlife and avalanches together into one project, as you will see. And with that, I will turn it over to Alden.
Awesome. Thanks for that great introduction, guys. Welcome to my master's thesis defense. I'd like to thank my committee, Jessica Lundquist and Bart Neeson, for being here, as well as the NASA IDS Interdisciplinary Research in Earth Science program for the financial support, and the Mountain Hydrology Research Group as well. So here is call it the million-dollar question that many people in the snow and hydrology space have asked. We know that in the past century and in recent decades, we've seen anthropogenic climate change cause warming temperatures in the Pacific Northwest and the Western US more broadly. And we know from our climate modeling studies that there is a lot of uncertainty about many things, including precipitation. But when it comes to temperature, we have high confidence that we'll continue to see warming temperatures in our future climate. So understanding this question, how will our snowpack change with these warming temperatures, remains important. A lot of research has gone into trying to answer this question. Some important findings include lower peak snow water equivalent values, or SWE, reduced days of snow cover, earlier snowmelt timing, and more precipitation shifting from snow to rain. And I want to take a step back and just think about these points and think about the type of snowpack processes that these points discuss. And they're really broad, big scale things, right? We're thinking about reduced peak snow water equivalent value. That's one number for the whole season. And that's, for a whole basin, that can just be one number. It's very broad, big scale hydrologic concept. And a lot of these big, large scale concepts use a modeled or a theoretical snowpack that looks something like this, where we see a soil layer and then our snowpack is just one big block. And it's kind of like a bucket, right? Where we can input precipitation and add mass, and then we can melt and remove stuff from that bucket. Although if you have ever skied or been out in the snow, that in reality, that's not what our snowpack looks like. It looks much more like this. It has a layered structure. This is a snow pit. This is about a meter deep snow pit. And all of these bright bands, there's some dust that kind of highlight some of these layers. But you can see that our snowpack has a lot of layered structure to it. It's not just one big homogeneous blob. And so when we're bringing it back to that bolded statement that we know more precipitation will shift from snow to rain, well, that has big implications for that layered structure of our snowpack. So let's just define some key terms first here. So what do we mean by snowpack structure? This is also referred to as stratigraphy. I use those words interchangeably in this presentation. And this refers to the layered structure of a seasonal snowpack. Similar to our layer cake, here, we have layers in our snowpack. Some layers are thicker than others, some are thinner than others, some have different densities. And in that snowpack, some of the important, most visible properties that we can see are crusts, are frozen water, that are really hard and compacted. And these crusts are some of the most obvious interfaces. In this analogy, you could say that the crusts are kind of like the frosting of a cake. They can either hold it together or they can cause it to fall apart. The crusts are really important. I want to throw back to this past weekend. How many people were out in the mountains last weekend? Did we see, or just out and about and noticed a lot of precipitation? Yeah, a lot of people. So we had it wasn't a very big atmospheric river, but we had a lot of precipitation. And that precipitation started as rain onto our existing snowpack. And then as the temperatures got colder throughout the storm, that rain then refroze into a melt freeze crust. And then the storm got a little bit colder, and then it shifted to some high density snowfall. And then in the past few days, we've just had lingering snow showers, and it's been really cold. So in our mountains, we've had even lower density snowfall on top of that. So we have this layered structure of snow, and this kind of tells the history of the weather history. The snowpack structure is really our weather timeline crystallized in the snowpack. So these crusts that we talk about, let's define those as well. So when I say crust, there are several different types of crusts, and these are defined in the International Classification for Seasonal Snow on the Ground by Charles Fears et al., and the Snow, Weather, and Avalanche Guidelines from the American Avalanche Association and Ethan Green et al. But among these types of crust. The one we're focusing on today in this presentation is melt-freeze crusts. And these are crusts that form when you have melt water in the top part of the snowpack, either from warm temperatures or from rain on snow events that doesn't percolate all the way through. It remains in the snowpack, and then it gets cold and it refreezes as a one thick, like very high density ice crust. And these are melt freeze crusts. The reason why we're focusing specifically on these melt freeze crusts is because their frequency is impacted by warming temperatures. Throwing it back to that bolded point that we're going to be returning to, that shift from snow to rain in warming air temperatures, the way that we can evaluate how that impacts snowpack structure is through the frequency of these melt freeze crusts. This is the aspect of the snowpack that is greatly impacted by this precipitation shift. The more rain on snow events, potentially the more crusts. And so we can use this as a proxy for understanding how that shift impacts snowpack structure. Moving forward in this talk, when I use the word crust, I'm just going to be using that interchangeably with melt freeze crusts in particular. So just if you hear me say the word crust, it's specifically melt freeze crusts. What does that look like in a snow pit? Hopefully this shows up on the projector here, but this is a buried melt freeze crust from a rain on snow event this past November at Stevens Pass. And if you can see about a third of the way up from the bottom, there's about 5 centimeters thick. You can even just see it's a little grayish, it's different color. And you can just visually see without even having to touch the snow. You can see these melt freeze crusts, the pretty notable features of our snowpack. Why do we care about all this? We know that those big picture things are relevant for hydrology and water resource management. Why do we care about the detailed structure of snowpack? Well, there's a couple reasons for that. We first care about wildlife biology. We know previous research has shown that knowing the snowpack structure and these melt freeze crusts impacts the movement patterns and predator-prey interactions of wildlife in our mountains, and in addition to their ability to forage for food. For avalanche forecasting and mitigation, this snowpack structure is critical information for avalanche forecasters to understand how sensitive a slope is for triggering an avalanche. And for recreation, because in general, more ice in your snowpack equals worse skiing, snowmobiling, and snowshoeing. And nobody is going out in the mountains hoping to go ski on ice. So here we have a video of Mr. Moose. And before I play the video, I just want you to think in your head, just watch, how does the snow impact Mr. Moose? Is there any way that it changes his life? So we can see that the snow actually has a big impact on Mr. Moose. The places where there are denser snow, perhaps with a crust, he can walk on the surface, no problem. But then when he goes away from that crust and sinks through, it becomes a lot harder for Mr. Moose to walk across the surface. So again, the snowpack structure matters for wildlife. There's a lot of research that has shown how this snowpack structure impacts wildlife. A lot of herbivores, they dig through and paw through the snow to get to the buried dried grasses and other vegetation buried under the snowpack. And when you have these ice layers formed from rain on snow events or other melt freeze crusts, they can decrease food availability because these animals can no longer get to their food supply. This creates a bottleneck. Food is already the bottleneck for a lot of these large herbivores, such as elk, moose, and deer in the wintertime. So further limiting their ability to access their forage increases winter mortality for these herbivores. Of course, then there's an inverse impact on predators. When you have more herbivores dying because they can't access their food during these crust events, then the predators actually do a lot better because they have more food supply. And additionally, these ice layers can boost the predator hunting efficiency. The animals that like to chase their prey down, such as wolves, they have easier movement when you have these ice layers present and can chase their prey down better. Again, going into more detail about how this is relevant to avalanche dynamics, snowpack structure is, again, critical information for avalanche forecasters. And in the Pacific Northwest, but also everywhere, crusts are an important piece of the stratigraphy or snowpack structure puzzle. And the reason for this is that they can develop weak faceted snow above or below the crust. And this weak snow can be a place where avalanches can be triggered and propagate through. These crust-related instabilities can then persist within the snowpack for long periods of time. I wanted to highlight here, this is a recreational avalanche forecast from the Northwest Avalanche Center from this past March. And here they say you can still trigger a large unsurvivable avalanche buried 2 to 4 feet deep on weak snow above a crust. And why I highlighted this in particular is because this crust formed more than 30 days and was buried more than 30 days before this avalanche forecast was issued. So this crust, once it was buried, it didn't go away. It remained a problem within the snowpack. So these crusts are really important pieces for avalanche forecasters to stay aware of. Just this last weekend, we looked at our puzzle pieces fitting together from the storm last weekend, and we know there was a crust. And here is an example of a size D2 skier triggered avalanche from February 1st that ran on that crust. And size 2 is that's a large avalanche that is big enough to bury or kill a human. And this is at White Pass, and these photos come from Dallas Glass with the Northwest Avalanche Center. But just this last weekend, we can see that crusts are important for telling this story. So going back, this is our statement that we return to. More precipitation is shifting from snow to rain with warming air temperatures. So how do we use that to define our research? Well, we can ask the question, how do we think that this is going to impact our snowpack structure and our crusts? And before we can begin to peel that back, we need to first understand, how do crusts form? We can develop our hypotheses by working through the process of these crusts. So we're going to work through here at Snoqualmie Pass from this period in December and early January, this past winter. And this plot here, we have air temperature here on the left y-axis in degrees Celsius, and this is our blue line. And that dashed black line is our 0° C mark. And then these light green colored box plot, or this bar graph, is with the y-axis on the right side, and that's our precipitation in millimeters per day. And why we wanted to focus on this is because we see here this seesawing pattern where temperatures are going above and below freezing temperatures very frequently. And that's occurring at the same time that we're having precipitation. And so we think about how crusts form. They require that liquid water present at the top of the snowpack that then refreezes. So we can begin to develop an intuition as to, we look at our temperatures and our precipitation and begin to think about, okay, now let's take a step back and let's look at our snowpack. What would we think that it would look like knowing these temperatures? And we can highlight this period, and this is our modeled snowpack, kind of a representation of what our snowpack looked like. To orient you on this plot, our y-axis here is snow depth in meters, and our color fill here is our snow density in kilograms per meter cubed. And all of these like striations that you can see, all these lines, these are individual layers within the model and within our snowpack. And the higher, brighter colors, those greens and yellows, those represent our crust. Those are high density snow. And we can see that we look at that seesawing pattern through our air temperature profile, and we can kind of highlight some of these events. So here are 3 different times when you have that air temperature seesawing between above and below freezing temperatures while you're also receiving precipitation. And we can see that at the same time in our snowpack density plot, we also see on the left here crusts form, those thin, lighter colored density layers. So that's kind of what we saw at Snoqualmie Pass last winter. But here's a hypothetical. What if we had warmer air temperatures? What would happen? And we can take a look. So now we're looking here. This is the same plot as the top right with our temperature, observed air temperature, and our precipitation at Snoqualmie Pass. But now we added in 2°C warming, and this is uniform across every single hourly time step. And we can see now that there's now some periods where our snowpack, or our site here at Snoqualmie Pass, goes several days, if not weeks, without going below freezing anymore. So now in this scenario, we might not think that this is going to create crust because we no longer have that refreezing. And seeing these seesawing temperatures and this pattern, and now understanding a little bit more as to why we are forming crusts, we can then develop some hypotheses. So our hypothesis 1 is that increased rain and more melt will refreeze, forming more crusts with warming air temperatures. And inversely, our hypothesis 2 is that then the snowpack stays too warm and to refreeze frequently, and that results in less crusts. And when we say too warm, what I mean by that is isothermal temperatures where the snowpack is remaining at freezing for long periods of time without actually refreezing, so it has liquid water present. And these little icons here, this 1 and this 2, these are going to pop up as we move forward through the slides, and we'll reintroduce those as they come up. So to start our modeling experiment and to start testing these hypotheses, first we need to choose a snow model. And we are, in this work, we use the structure for unifying multiple modeling alternatives, further referred to as SUMA. And the really great thing about this model is that it can be run as a point snow model with a really high vertical resolution, meaning that it represents many different layers. We ran it here with up to 100 layers, and these layers range in thickness between 1 centimeter and 5 centimeters thick. So it's a really great tool for analyzing this problem. This snow model, SUMA, was then run using the observed temperatures at a variety of different sites that we'll discuss in a minute for the years 2000 to 2024 to develop what we think is like a reasonable range of snowpack, of our snowpack properties, we have a nice range of some wet years, dry years, cold years, warm years. And then from that, we can simulate warming to do a sensitivity analysis to compare our snowpack structure. And the benchmarks here were 2 degrees and 4 degrees of uniform warming across every time step. In this, moving forward in this talk, I'm going to be showing results from the 2-degree warming scenario. I also have results from the 4-degree warming, so feel free to ask questions at the end, and I have some supplemental slides that I can show those results if people are interested. And then we can compare this stratigraphy in our warming scenario and our observed model runs and test our hypotheses to see how they compare. So to orient you onto our domain, we are looking at the greater Pacific Northwest region, and this is showing a mean winter air temperature and precipitation from PRISM 4-kilometer product this December through February. And on the left here, this is precipitation in millimeters. And we can see the Cascade Mountains that are labeled there are a pretty stark, important feature here. To the west of the Cascades, we see pretty high precipitation, winter precip in excess of 2,000 millimeters, and relatively mild air temperatures. On the right, we see light colors, many places in our mountains near freezing, even in snowy locations. As one moves east through our domain, temperatures decrease generally, and precipitation decreases as you move away from the Cascades and the Pacific Ocean. The site selection, we used 53 NRCS snow telemetry sites for this work, and we chose each snowtel that was located closest to a ski area in Washington, Oregon, Montana, Wyoming, and Idaho. And we chose near ski areas because this is representative of where humans live, travel, and recreate in the wintertime. And additionally, because snowtels near ski areas are generally rather accessible comparatively, so they can be better maintained than some of the other snowtels that are in more remote places. On the right here, we see our all of our 53 sites and their elevation plotted with the color fill, and we can see we represent a range of elevations and geographic area through this domain. So thinking about our model and how that modeling process works, to start out, we have 7 meteorological inputs. They are air temperature, incoming shortwave radiation, wind speed, incoming longwave radiation, specific humidity, precipitation, and air pressure. And these 7 meteorological inputs are then put into our numerical solver within our model. And through some parameterization choices and model decisions, we fine-tune the model. We then have our output from SUMA. And there are many different output variables that you can extract from this modeling work. The ones that I wanted to highlight here that we'll be discussing today are layer density, temperature, thickness, and depth. So for each individual 1 to 5 centimeter thick layer, we can extract each of these properties at each hourly time step. Where do these meteorological data sources, these 7 variables, come from? Well, we have a temperature evaluation that we'll discuss and a density evaluation. And for the temperature evaluation, this is for Kettle Ponds, Colorado, we used observed variables or observed values from the Sublimation of Snow, Lundquist et al. 2024 data set. And then for our density evaluation, we used observed temperature and precipitation, and then empirically derived the other 5 meteorological inputs. And for the SNOTEL sensitivities, they remain the same as a density evaluation at Snoqualmie Pass, which we also have observed temperature and precip and empirically derived the other 5 quantities. So that temperature evaluation, we wanted to test to make sure that our model was adequately representing our snowpack processes. So we're doing this at Kettle Ponds, Colorado. And the reason for this is because it is really, really hard to measure snowpack temperature over a continuous time period in situ, because any place where you have those melt freeze crust and frequent refreezing, it just breaks instruments. So there are very few, if any other data sets like this where we can measure in situ snowpack temperature at each time step. And we're very grateful that we had the access to this data set. So we're comparing at Kettle Ponds. And I don't have any slides here, but again, if you have any questions about that temperature evaluation, I have slides in the supplemental section that I can show at a later date. For our temperature or our stratigraphy evaluation, this was done at Snoqualmie Pass, Washington. And this was done using manual snow pit measurements from the Washington State Department of Transportation. I want to give a huge thank you to John Stambaris and the whole Washington DOT team for going out, and they dig 1 meter snow pits every single day during the winter and have been doing this for many years. And this is an excellent data set that we can use to compare to our modeled snowpack stratigraphy. That snowpack stratigraphy, we can evaluate using these manual snow pits. And what do we actually care about? We're not totally interested in everything from these snow pits, but we're specifically interested in that frequency and the duration of these melt freeze crusts. This is what matters to us. How do we measure this? We can use a test called the hand hardness test. And this is resistance to deformation from sticking into the snow with a variety of different instruments. Here is a wonderful cartoon, courtesy of the National Avalanche Center. And here are the different, the snow hardness scale ranges from fist, forefinger, one finger, pencil, and knife hardness. And you poke it in the snow to see how hard it is to push that snow out of the way. And so this gives you a relative profile of snowpack, knowing where are the harder layers and where are the softer layers that we can then compare to our model and help us identify the crusts. This hand hardness scale is defined in that International Classification of Seasonal Snow on the Ground, but it is widely used in the avalanche industry and is a great tool for avalanche forecasters. So our model stratigraphy comparison, we then can compare those hand hardness measurements to our modeled SUMA output. And how we defined the crust was an increase of depth in density at a depth with greater than 150 kilograms per meter cubed in 3 layers. So that's a maximum of has to be a minimum of 150 density change and a maximum of 15 centimeters as one moves down through the snowpack. And through this, for each time step, we can develop a daily binary. So asking each day in our model, was there a crust at any time step, yes or no? And running this from December 1st through March 31st of water year 2024 at Snoqualmie Pass. So here is some model output from that water year to orient you again. This is snow depth on our y-axis and snow density in the color fill. And these bright striations are a layered structure. And the Washington DOT snowpack stratigraphy was in the top 1 meter of the snowpack. So that's what we compared with the model. So I wanted to highlight some times. So we have a little cartoon hand. Here is a time, a day in mid-December, where we had 4-finger snow, pencil hard snow, 1-finger snow, and then pencil hard snow. And that was the observed stratigraphy from the snow pits. And then we can see in our observation or in our modeled results that we have a very thin, high density layer about 15 centimeters below the surface, which is where the Washington DOT avalanche workers found that pencil hard layer. So we can see that agrees well with our model. We can also look at a period in January where we had only new snow, low density snow in the top 1 meter of the snow pit, ranging from fist to 4-finger to 1-finger hard snow. And we see in our SUMA output as well, it's all these dark blue and light blue colors. So it's relatively low density snow with no obvious crusts. And then in early February, that avalanche forecast I showed was talking about this crust that formed in February of 2024. And here it is. This crust we can see was a knife hard layer in the snow pit observations, buried about 10 centimeters below the surface. And we can see in our model output too, we have a very high density band right at that depth, about 10 centimeters below the surface. So we can see that our model just visually does quite well with matching the observations. In summary, how did that model do across the whole season? Well, our algorithm correctly identified crust or no crust on 81% of the days. This was a relatively crusty winter. There were most of the days had crusts at this site, but in total, we predicted the correct value 81% of the times. All right, so now we've set up our model and we've talked about our stratigraphy. Let's define some metrics that we're going to use to evaluate moving forward. So there's a lot going on with this plot. So let's take a few moments to orient ourselves. Here we see on the left side, this is our SUMA model depth and density for Harts Pass, Washington for water year 2024 with snow depth on the y-axis and the color fill being our density. And the left side is our observed air temperatures. On the right side is the same meteorology for this Harts Pass site for this water year 2024, but we warm 2 degrees Celsius at every time step. And we can begin to identify with that 150 kilograms per meter cube threshold, how many days during this winter between December 1st and March 31st do we see crusts? In our observed air temperature version on the left, we see crusts were identified 24 of the days during this period. And it's kind of maybe hard to see on the projector, but there's like a thin crust in late December and maybe some crusts going on in late March. But overall, there were not very many crusts. It was pretty low density snow. Moving over to our 2-degree warming run, now we have a lot more crusts. We've more than tripled the days with a crust with 2 degrees of warming. And this is just looking at that December 1st through March 31st period. But now we can develop a percentage. How much of this period did it have a crust? So in this water year 2024, there were 122 days between December 1st and March 31st. So we can divide our number of crust days by that length and see that we had 20% of the observed air temperature run had crusts and 65% of the 2-degree warming run had crusts. So more than threefold increase in crusts in 2-degree warming. So we can see that this kind of agrees with our hypothesis number 1. Here is a cold upper elevation site where with 2 degrees of warming, we see more crusts. So yeah, this agrees with our first hypothesis that we see more crusts with warming air temperatures. Now let's look at a different site with different meteorology. Go back to Snoqualmie Pass. This is again looking at the water year 2024. We have snow depth on the y-axis and snow density in the color fill. And again, we have observed air temperatures on the left plot, and then the same meteorology just with 2 degrees Celsius of warming on the right plot. And here it's a little bit different a story. We see in the observed air temperature model run, we now see 95 days during that 122-day period had crust. So most of the winter had crusts, and we can just visually see that. We see all these bright colored striations in our snowpack of those high density crust layers. In our 2 degrees Celsius run, we see 36 days now, and this is a little bit different story. So let's think about why that might be. Well, I want to highlight this period down here in December where we see relatively high density snow on the ground, but with not very any distinct layers. And we can think about, we looked at the observed temperature during that period earlier on, and we saw that there were frequent periods where we go a week or two without going below freezing. So our snowpack at this time was isothermal. It had liquid water present. It was not refrozen. It did not have any crusts. And thus, with warming air temperatures at this site, you just didn't have enough refreezing to get these crusts. And then, of course, we can do the same calculation and see that on the left observed air temperature plot, we had 79% of the winter had crusts versus only 30% of the winter in the perturbed warming run had crusts. And this now agrees with our second hypothesis, right? This is a different site. It's a warmer, lower elevation site, less refreezing, less crust with warming. This agrees with hypothesis number 2. And we can dive a little bit deeper into this. So this is a similar plot to what I've been showing you, but now we're looking at snowpack temperatures. So our y-axis is still snowpack depth, and now the color fill is our snowpack temperatures. And this is, again, Snoqualmie Pass with observed air temperature model output on the left and with 2 degrees Celsius of warming on the right. And I want to highlight these periods where we see these just solid purple colors. And these are times when the whole snowpack profile is isothermal. It's all at 0C. And we see that happen in December in our warmed run. We see that there, for most of the winter, other than this January period, there are pretty infrequent times when the snowpack is not isothermal. And we can calculate some metrics based on that. So first we can look at how many days with snow cover there were. And this is just how many days with any measurable snow cover in our model. And there were 248 days of snow cover with the observed temperature, and a drastic reduction with only 162 days with snow cover in the warmed run. And then we can also then calculate the percentage of our winter that had isothermal temperatures. So in our plot on the left with our observed meteorology, we see 18% of the winter was isothermal and 69% of the winter with 2 degrees of warming had isothermal temperatures. And again, this agrees with our hypothesis too, and this maybe explains why we're seeing these diverging hypotheses. So now we can use these metrics that we've defined, our percent of the winter with crusts, to evaluate changes across our broader domain. First, we can look at the number of crust days in our current climate. Here, each dot represents our site, and the color fill represents the number of crust days between December 1st, excuse me, and March 31st on average for that 2000 to 2024 period. And then we can look at the percent change in crust days. So this is just subtracting the percentage of crust from the 2-degree warming run from the current climate run. The color fill here denotes the percent change between the warmed run and the current climate one. Where you see those upward facing arrows in the blue colors, these are places where we see more crust with 2 degrees of warming. And these are places that agree more with our first hypothesis. The places with the red triangles that face downwards, those agree more with hypothesis number 2. And these are sites where we see a decrease in our melt freeze crusts with warming air temperatures. So you might look at this and notice there's a little bit of a geographic trend appearing in our data. We see that, especially in Western Washington and Western Oregon, most of our sites have decreasing crust with warming, while in our colder places, potentially inland, further inland, in Eastern Oregon, Idaho, Wyoming, Montana, most of those sites have an increase of crust with warming. So what we can compare, let's turn this into a scatter plot and compare the percent difference of crusts between the two model runs with the climatology of each site. So this here is on the y-axis is the percent change in the number of crust days between the 2-degree warming run minus the current climate run. And this is the same as this percent difference shown here on the right, just in the scatter plot on the y-axis over here. On the x-axis here, we have current mean winter air temperature at each site. And we can start to see some patterns emerge in our scatter plot here. We can take a closer look, and we can see that our colder sites in the top left, where our current mean winter air temperatures are in the -6, -8 degrees C range, most of those sites have an increase in crust with warming. And these are places that agree more with hypothesis number 1. There's also all these sites down here in the bottom right quadrant, where we see our mean winter air temperatures between, say, 0C and -3 or -4C. And all of these sites have a decrease in the percent of the winter with crusts with that 2-degree of warming threshold. And these are places that match our second hypothesis. So we can start to see a story emerging here that there's not one uniform answer. We actually have some places that match each of our hypotheses. And yeah, there's not one answer to answer our research question. And now we can project this across. So what we're looking at here is using that prism climatology. We know the current mean winter air temperature, and we can develop our cluster and our threshold for what do we consider a warm site versus a cold site. The warm sites are in this red box, and our threshold here is sites with a mean winter air temperature in the current climate of warmer than -3°C. And those are outlined in red on our plot on the right. And these are sites where we'd expect to see fewer crusts with that 2-degree warming threshold. All of the blue colored fill on the right plot, these are places with we're defining as our colder sites, places with a mean winter air temperature in the current climate of less than -3°C. And these are places where we might expect to see more crusts in a warmed climate. We can also identify this from our isothermal temperatures. Remember, we looked at our percent of the winter with those isothermal temperatures, and now we can compare this to our current mean winter air temperature. And we can highlighted here that cluster, those warm sites that we defined of that -3°C threshold. And those up here have the greatest increase in the percent of their winter with isothermal temperatures. So we can see that that may be the reason why these warm sites have fewer crusts. They're isothermal for longer in the warming climate versus on the bottom left, these colder sites have not as big of an increase in isothermal temperatures. And again, our percent isothermal equation here is just dividing the number of days in the snow-covered season with isothermal temperatures divided by the number of days with snow cover. So what do these results mean? What does this matter? How does this matter for the things that we care about? And this is our avalanche forecasting, mitigation, and our wildlife biology applications. So here's that same plot where we're mapping those clusters, those warm sites versus our cold sites across our domain. And these places in red with places with the fewer crusts, if we remember, those herbivores do a lot better when they can access their food. They don't like digging through the crust. They need to be able to eat. And so the places in red with fewer crusts, we can see that herbivores may benefit in these regions. They'll have more access to their food for longer of the season. Of course, the opposite will be true in places with the blue color fill. These are places where we'd expect more crusts with warming, and these are places where predators benefit. If we start seeing warming air temperatures and more melt freeze crusts in these colder places in the interior of the continent, the herbivores are going to have a lot harder time accessing the food, and the predators may benefit from this. What about avalanches? So here's again the same plot. Our red is our warm sites, and our blue is our cold locations. In the red regions, where we see fewer crusts, we could maybe say that we'll see more wet snow avalanche problems. And these wet snow avalanche problems occur when we have an isothermal snowpack. That is when our liquid water present in the snowpack acts as that lubrication. And so having more of the winter at an isothermal snowpack may lead to more of these wet snow avalanche problems. And we can kind of see that this is generally speaking the western part of our domain, the warmer locations. And the opposite may be true in the colder places. These are places with more crusts. And I think it's interesting to highlight this, especially this week. In the last week, we've seen a major inland penetrating atmospheric river drop a lot of rain in weird places in Wyoming and Idaho and create these melt freeze crusts. And when that happens, perhaps the Wyoming Department of Transportation, they're getting avalanche forecasting problems that they just don't see very frequently. It's a shifting paradigm, and they don't know what to do. So maybe they call John Stambaris at Washington DOT and start saying, well, what the heck do we do with this? We don't see these problems. We're seeing a changing snowpack structure. And sometimes these crusts, they can be more challenging for forecasting and for passive mitigation. So we can jump back and review our hypotheses once more. Our hypothesis 1 is that our rain and our increases in rain and liquid water from melt will refreeze within the top of the snowpack more frequently and cause more crusts with warming air temperatures. Hypothesis 2 is the opposite, and that's where the snowpack stays too warm to refreeze, it stays isothermal for longer, and you end up with less crusts. And then returning to our research question that we asked at the beginning. How will the snowpack stratigraphy be sensitive to warming air temperatures? Well, as we've seen, there really isn't one answer. It depends on where you are. I want to close with a quote from Jessica, who has said this many times, but my snow is different from your snow. You can't, it's hard to make large claims and say like, well, across the board, we're gonna have more crust or less crust with warming. It depends on where you are because snowpack and climate varies quite widely across geographic space. And I want to close with that and thank everybody who has supported me along this journey, especially my advisor, Jessica Lundquist, but everybody else on the slide and many, many more people. I would not have been able to accomplish this work without you. So thank you to everybody. And with that, I'd love to take any questions.
So we will take questions from the general audience first, and then the general audience will leave, and then the committee will ask more questions after. It's all within the general audience. Everything.
Yeah.
How does the change in crust overlay with the distribution of your herbivores? You know, is that something that you've looked at as part of this research in terms of seeing how the predator-prey relationship changes in these geographic regions? Is there a difference in distribution of those species, or is that beyond the scope of this work?
I think it's a little bit beyond the scope. I personally am just kind of interpreting the previous wildlife biology work, but I think that there are large predators like cougars across the entire domain, as well as a lot of herbivores like deer and elk, and those are pretty ubiquitous across the domain. In terms of current trends as to whether or not we've already seen this happen, I can't speak to that, but it's an interesting thought. Thank you. Yeah.
How do you think your change in isothermal days would, I guess, change if rather than using full snow cover days, you just use the winter time, since your springtime is likely going to be isothermal because you're warming, like melting that snowpack.
Yeah.
Did you look at just looking at the winter time?
Yeah, it's relatively a similar pattern because snowpack melt is driven by solar radiation generally. So yeah, I mean, I could have looked at that specifically, but it's a similar trend. That the reason why we see that increase in isothermal temperatures at our warmer sites is not really any change on the melt side on the spring or the fall. It's more during the winter. It's warmer for longer. Thanks. Yeah.
Can you go back to the time depth thought for skin-foaming pads?
Yeah. Are you interested in? Oh, yes.
Yeah. So, right, it's like the one you were previously on.
Oh, the two panel.
Yeah.
Yes. Yep.
Yeah, in the warming scenario, despite there being fewer crusts, it almost, I mean, it's just me eyeballing, it almost looks like the individual crusts themselves are thicker.
Yeah.
You've looked at, and does that change like the herbivore/avalanche implications?
I haven't looked at the thickness changing, but I think that's a great point. I mean, just visually, that crust is a lot, and I think that has to do with an isothermal snowpack. More of that meltwater percolates deeper in the snowpack, so you get deeper crust or more thick of those ice layers. But yeah, that's a good point. That'd be a great thing to look at, is like how does that thickness change? Yeah.
So my impression is that this analysis was done looking at warming temperatures, holding other all factors constant. Is that right?
Yes.
Yeah. So I imagine that like with climate change and things like that, the increases in temperature could be confounded with other changes in atmospheric conditions, those of which could also have influences on like snowpack structure and formation
totally.
of crusts. And I mean, that would be like a really hard question to answer, because like who knows how like warming temperatures will influence all these other things, and those other things could also influence crusts. But like, how would you go about like trying to get an understanding of that question? Like, if you have any ideas on that?
Right. So the reason we specifically looked at just changing a sensitivity to warming air temperatures is because climate models, there's a lot of uncertainty for those other variables like precipitation trends over complex topography. So the one thing that we know we have high confidence in is all those warming temperatures. It'd be really challenging to really even pick out any trends as to whether or not we'll see more or less precipitation. The latest CMIP6 climate model intercomparison project showed anywhere from an increase of 20% precipitation for Washington to a decrease of 20% of precipitation of Washington. So to try to draw any conclusions to then test the sensitivity of snowpack, it'd be really challenging.
Online,
Yep.
we have some compliments, Steve Burgess, said excellent work and presentation. And same thing from Ming Hua Zhang. And then David Sheen asked a clarification question. Are the maps / results for the +2 degrees warming relative to current temperatures defined by recent 30-year norms?
So those 2 degree, yeah, so the question from David was, are the results for the +2 degrees Celsius warming run relative to current temperatures defined by those 30-year normals? And those are not relative to the normals, they're just at every single time step during the 2000 to 2024 period, just increasing the temperature at every time step 2 degrees. The PRISM map came from those 1991 to 2020 climate normals. Yes. So yeah, the perturbation is relative to the observed temperature at each SNOTEL site, and then we apply those to those trends on the PRISM map. Yeah.
Did the temperature change that you applied also change the phase of the precipitation?
Yeah, so that's what we're really seeing. Like when we see that the change in seeing more crusts and more in these colder places is because we're seeing the phase change from more of our winter precipitation switching to rain during the winter. Yeah, that's really what's driving this process.
Related to that, how did you think about like the rain snow partitioning in these?
Great question. Yeah, so I have a slide that I can show about that. So we leveraged some previous work done by Ryan Currier during the Olympics field campaign. And as part of this, Ryan used and co-authors used SUMA at Snoqualmie Pass in particular, and they chose a variety of different rain snow partitioning thresholds, and they found 0C to be the most representative. So yeah, really leveraging their work for this choice. Yeah.
Might be like an interpreting question, but depending on like the location that you're thinking about, how much do you think like the storm type, as in an area that's more exposed to ARs or something that gets, you know, smaller storms, how might that like play into the way that these crusts are created? I'm thinking particularly about like more inland continental climates that see fundamentally different storms than what you might see in a very maritime climate.
Right.
How do you think that might play its role with respect to, let's say, like avalanche
Right.
dynamics?
Yeah, I think there's some evidence to suggest that the frequency of atmospheric rivers and their intensity will increase. So perhaps these increases in precipitation, or this increase in the fraction of winter precip switching to rain will maybe be greater in those warmer locations that are more, or I guess further west locations that are more susceptible to atmospheric rivers. And perhaps that impact will be a little bit muted when you move further inland. You're thinking about like interior Montana, it's a lot harder to get inland penetrating atmospheric rivers there, so that effect might be more limited versus like, I mean, we just saw this past weekend, atmospheric river impacting like southern Idaho mountains. Is a lot more susceptible there. Thanks.
Questions? All right, then let's go ahead and figure.
Keep that on.
For break, you can get snacks and then go ahead and put the committee roll.
Sounds good.
We're going into the Microsoft Cafe.
Yes.
With the suitcase.
Like walked up.
Today or yesterday.
Oh, wow.
I
I was surprised.
My for program is kind of like negative, like math. Way is like, yeah, like if
I'm like.
Crazy to see it change. I think that.
Yeah, I get shut down.
Yeah.
That's so forever. Yeah, that's frustrating. Yeah.
That was great. I also didn't know.
Just, if we are doing video, oh, really, we're trying to, if there's any kind of
Energy.
there's
Yeah, energy.
whatever.
Thank you. Let me know what's the question.
Yeah.
Send our.
Yeah, exactly.
Yeah.
Yeah, no, I mean, that's pretty straightforward.
I know.
Cold water and. There's.
Remember, in a panic, you can always fight your committee instead.
Right.
Throw a solid like uppercut. They won't see you coming.
That's it.
Oh, yeah.
Can we do this later?
Yeah.
Celebrate you.
Oh, sorry.
Torture.
Sorry, I withdraw my.
Yeah.
You want any food?
I'm good.
Okay. Yeah, like, y'all need anything?
No.
Nice job, man.
Thank you.
You guys later.
Don't Eric can come in?
Only oranges and stuff.
I have a second one that was like.
Like what?
That was hard.
I'll say good. Sunshine.
It's pretty awesome.
All right.